Namaste, my friend, and welcome back to JEE Mathematics with Typical Monk. This is class 2, and today we meet a number the real line never had. Here is something worth sitting with for a moment. Every quadratic that refuses to touch the x-axis, every rotation you will ever compute, every wave you will meet far later in the syllabus. All of it rests on one small, strange idea, a number whose square is negative. When Sarah first heard that a number could square to give something negative, she assumed it was a trick question. It is not. It is a whole new plane waiting to be explored, the Argand plane. Today, one idea at a time, we step onto it and meet Iota for the first time. Take a slow breath. Let us begin. So what will you carry home from today's class? First, Iota and the powers of I, the cycle that repeats every 4 powers. Second, the algebra of complex numbers, addition, multiplication, the conjugate and the polar and Euler forms. Third, the modulus and the argument, how we read a complex number straight off the Argand plane. Fourth, the Moivre theorem, the cube roots of unity, the nth roots of unity, the triangle inequality and loci. And fifth, the G drills, a word problem, a match, and a short answer round. So everything you learn today, you can also score with. Ready? One idea at a time. Let us start with the raw material. Iota, written as I, is defined as the number whose square equals -1. The real number line has no such number. Every real number squared is positive or 0. So mathematicians simply invented one and gave it a plane to live on. Now watch what happens as we raise I to higher powers. I to the power 1 is I to the power 2 is -1 by definition. I to the power 3 is I to the power 4 is 1. And then, David noticed, the whole pattern repeats. I to the power 5 is back to I again. Every 4 powers, the cycle resets. Every complex number is written in the standard form, z equals a plus ib, where a is called the real part, and b is called the imaginary part. And its conjugate flips only the sign of the imaginary part, z bar equals a minus ib. Sit with that. The conjugate returns again and again. Now look at this diagram. Because it turns a complex number into a point you can actually see. A horizontal real axis, a vertical imaginary axis, crossing at the origin. Together they make the Argand plane. First, the plane itself. Lisa's complex numbers equals a plus ib, plots as the point with coordinates a and b. The real part tells you how far right or left. The imaginary part tells you how far up or down. Second, the modulus of z. This is simply the distance from the origin to that point, found the same way you would find any distance, the square root of a squared plus b squared. Third, the argument of z. This is the angle, the line from the origin to the point, mixed with the positive real axis. And while the ratio of b over a gives a first guess, you must adjust it for whichever quadrant the point actually sits in. And fourth, a rule G insists on. The principal argument is always chosen between negative pi, not included, and pi, included. Miss that range, and a perfectly correct angle can still be marked wrong. Now we learn to work with these numbers. First, addition and subtraction. You simply combine the real parts together and separately combine the imaginary parts together, nothing more mysterious than that. Second, multiplication and division. Multiplication expands normally and then uses I squared equals -1 to tidy the result. Division multiplies both the top and the bottom by the conjugate of the denominator. So the bottom becomes a plain real number. Third, the polar form. Instead of a plus ib, John can write z as r times cosine theta plus I sine theta, where r is the modulus and theta is the argument, and the Euler form r times e to the power I theta is exactly the same idea written one letter shorter. And fourth, 2 results worth remembering together. The triangle inequality says the modulus of 1 plus 2 is at most the modulus of 1 plus the modulus of 2. And a locus like the modulus of minus equals r traces out a perfect circle centered at A. time to solve a full problem together, slowly, the monk's way. Evaluate 1 plus I, the whole raised to the power 8, using de Moivre's theorem. Step 1. Write down what is given. Z equals 1 plus I, and we need Z raised to the power 8. Step 2. Find the modulus. It is the square root of 1 squared plus 1 squared, which is the square root of 2. Step 3. Find the argument. Both the real part and the imaginary part are positive and equal, so the point sits exactly in the first quadrant, at an angle of pi by 4. Step 4. Apply de Moivre's theorem. Z raised to the power 8 equals the modulus raised to the power 8 times cosine of 8 times pi by 4 plus I sine of the same angle, and 8 times pi by 4 works out to 2 pi. Step 5. The answer. The modulus raised to the power 8 is 16, and cosine of 2 pi is 1 while sine of 2 pi is 0. So 0 raised to the power 8 equals 16 exactly. Notice the path. Given, modulus, argument, de Moivre, answer. The same steps unlock every powered question G can ask. Now, the heart of the chapter. How powers turn into rotations. Look at these two circles. The unit circle on both sides. First, multiplication by I. Take the point 1 sitting on the positive real axis and multiply it by I. It lands exactly at the top of the circle, rotated 90 degrees anti-clockwise about the origin. Multiplication by I is nothing but a rotation. Second, de Moivre's theorem in its cleanest form. Cosine theta plus I sine theta raised to the power n equals cosine of n theta plus I sine of n theta. Every power simply multiplies the angle. Third, the cube roots of unity. Solve z cubed equals 1, and you get 3 points spaced perfectly evenly around the unit circle, 120 degrees apart. Call them 1, omega, and omega squared. And fourth, the property that makes them so useful. 1 plus omega squared equals 0, and omega cubed equals 1. Remember that pair. G returns to it constantly. Now sit up straight. These 5 lines are what G actually asks, year after year. 1. Learn the omega properties cold. 1 plus omega squared equals 0, and omega cubed equals 1. Half the roots of unity questions collapse the moment you recall this pair. 2. De Moivre's theorem extends naturally to roots. The nth roots of unity are simply endpoints, equally spaced around the unit circle. 3. The triangle inequality. The modulus of a sum is at most the sum of the moduli, with equality only when the two complex numbers point in exactly the same direction. 4. Loci. The modulus of z minus a equals r describes a circle centered at a with radius r, while the modulus of z minus a equals the modulus of z minus b describes the perpendicular bisector of the segment joining a and b. 5. The principal argument always lies between negative pi and pi. Read the quadrant carefully before you trust the arctangent ratio alone. Let us drill the G way. I read a claim, you decide true or false, and if it is false, find exactly where the reasoning breaks. First claim, I raised to the power 4 equals I. Let us check. The cycle we built earlier runs I minus 1 minus I 1 and then resets. So I to the power 4 is 1, not I. This is false. The cycle closes after exactly 4 powers, and it is 1 that closes it. Second claim, the modulus of a complex number can be negative. Think carefully. The modulus is a distance from the origin on the Argand plane, and a distance is never negative. So this is false. The modulus is always 0 or a positive real number. Third claim, omega squared equals the conjugate of omega. Check the reasoning. Omega sits exactly on the unit circle, so its modulus is 1, and since omega cubed equals 1, the conjugate of omega must equal 1 over omega, which is exactly omega squared. This one is true. Omega squared truly is the conjugate of omega. A quick match now. Say each answer aloud before I reveal it. I raised to the power 13, divide 13 by 4, the remainder is 1. So this equals I itself. 1 plus omega squared. This is the classic identity, and it equals 0. Omega cubed. Since omega is a cube root of unity, this equals 1. And the modulus of 3 plus 4, the square root of 3 squared plus 4 squared, which is the square root of 25, so it equals 5. If all 4 came to you before the reveal, complex numbers are becoming yours. Here is a favorite G format. I read some statements. You silently count how many are correct. Statement 1. The conjugate of a plus IB is a minus IB. Hold your verdict. Statement 2. A complex number on the negative real axis has argument 0. Think before you answer. Statement 3. Multiplying a complex number by I rotates it 90 degrees anti-clockwise. So, how many are correct? 2 statements, the first and the third. The conjugate truly does flip only the sign of the imaginary part, and multiplying by I truly does rotate a point 90 degrees anti-clockwise. But the second one falls. A point on the negative real axis has argument pi, not 0, because it points in the exact opposite direction to the positive real axis. 2 correct, statements 1 and 3. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. The modulus of z1 plus z2 always equals the modulus of z1 plus the modulus of z2. It feels natural. Surely distances just add up? But here is the truth. That equality only holds when z1 and z2 point in exactly the same direction on the Argand plane. In every other case, the triangle inequality gives you a sum that is strictly smaller. The 2 vectors partly cancel each other. Myth 2. The argument of a complex number is just the arctangent of b over a and nothing more needs to be checked. The truth that ratio alone can quietly place you in the wrong quadrant. The true argument depends on the actual signs of a and b and must be corrected by adding or subtracting pi when the point does not sit in the first quadrant. Time to test yourself. Rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just the ideas you built today. Question 1. What is the real part of the sum of 2 plus 3i and 4 minus 5i? Add the real parts. 2 plus 4, 6. Question 2. What is I raised to the power 7? 7 divided by 4 leaves remainder 3, and the third position in the cycle is minus I. Question 3. What is the modulus of the real number 5? A real number has no imaginary part, so its modulus is simply itself. 5. Question 4. What is the argument of I, the purely imaginary positive number? It sits straight up on the imaginary axis, so its argument is pi by 2. And question 5. How many distinct cube roots of unity are there? Exactly 3. 1, omega, and omega squared. If you caught all 5, you have truly understood today's class. Let us gather the whole class in one slow breath. Iota is the number whose square is minus 1, and its powers cycle every 4 steps, I, minus 1, minus I, 1, and then it repeats. Every complex number is z equals a plus ib. Its modulus is the distance from the origin, and its argument is the angle from the positive real axis. The polar and Euler forms write c as r times cosine theta plus I sine theta, the same point described through a rotation instead of a pair of coordinates. The Moivre's theorem turns powers into rotations, and the cube roots of unity satisfy 1 plus omega squared equals 0. The triangle inequality bounds the modulus of a sum, and a fixed modulus, measured from a point, traces out a circle as its locus. And next class, we step into quadratic equations, the discriminant, the sum and product of roots, and the tricky question of common roots. Do not miss it. And so, my friend, we have taken the second step. It may have looked like just a strange square root of a negative number, but understand this. The complex number you met today reappears in equations, in vectors, in rotations, even far later in signals and waves. Sarah, David, Lisa, and John all once stared at I squared equals -1 and wondered how a number could do that. Today, so did you, and now you know the answer. Be patient with yourself. Tonight, revise the cycle of powers of I. Once, slowly, until it is automatic. One idea at a time, you will crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you among the quadratics.